has. So we can probably just run through this real quick. I don't want to spend a whole lot of time doing this because I want to get to the programming part. But go ahead and take out a sheet of paper. And what you want to do is you want to use the relay contacts that we talked about in the last class to implement these logic functions. Now, remember, we can use switches in series or switches in parallel to represent AND logic or OR logic. But what we do is we use relay contacts. And I showed you what a normally open contact look like and a normally closed contact look like. So instead of using switches, implement these Boolean expressions using the relay contacts that we discussed. And then today, when we get into the PowerPoints, we'll show you the symbols, the actual instructions that you use when you write programs. And you're going to see that they're really similar to normally open and normally closed relay contacts. So I'm going to give you just a couple minutes to do these, and I want to get into the PowerPoint. So go ahead and just get a scrap piece of paper, and you want to write these ladders out using those normally open and normally closed relay contacts. So I'll give you, I don't know, maybe 5 minutes, and then we'll come in and we'll take a look at them. So see what you can do with this, and then we'll discuss it, and then we'll move on into the lecture. All right, guys, about 30 more seconds, and then we'll take a look at the problems. All right, so we have these Boolean expressions, and we want to implement these expressions in what we call a ladder, a control ladder. And so we mentioned that the way you can think about control in a ladder, electrical ladder, is you have these two vertical wires, and instead of having a power source, we just think of we just have what we call line 1 and line 2. And we'll think of when I bridge this with a wire or with some symbols, if I have a closed path, then think of, for now, just think of current flowing from L1 to L2 if there's a complete path. And so if I want to implement this, this is, of course, the first one. That's a logical AND. Remember that dot is a logical AND. And if I was using switches, I put those two switches in series. But since we're using relay contacts, the first rung would look like this. Those are my inputs. And then the output is always the last thing on your rung, the furthest thing to the right. And then I just label this A, B, and Y. So the first rung of that first Boolean expression, implemented as a ladder, would look like this. The other one over here, that's OR logic. So remember OR logic says I have switches in parallel. Only one path needs to be closed in order to get an output. And so I'll show the same switches A and B. But this time I'll make a branch like that. Contact A, contact B. My output is always the last thing to the right on the rung. So then after that, they get a little more complicated, but really nothing too bad here. So here we have, this time I have an OR and I have an AND. And you can really show that in any order, but we'll just take it the order that is shown in the expression. So I have this branch, and this would be contact A, contact B, and I AND that with C. And I have my output Y. So that expression, the control ladder for that is as shown. This one is kind of the same, but we just flip the OR with the AND. So I can take A and B. Then that whole thing, that whole quantity is ORed or parallel with C. So that control ladder looks like that. And then this one looks like I have two ANDs, and they're ORed together. So I got two series contacts. A, B, and two more series, C, D, and they're ORed together. My output is Y. This one, the way we're going to implement a NOT is, this is a normally open contact. If that's A, and I'll show A NOT. We're putting a cross through it like that. That represents a normally open contact. This represents a normally closed contact. Now today, when we get to the PowerPoint, the actual instruction that we're going to use is going to look kind of like that. It looks exactly like this in the simulation software, but at that point, you don't want to think of this as normally open and normally closed. The switches or buttons can be normally open and normally closed, but we'll have specific names for these that look for a specific binary value, but we'll get to that. So I think, so if I want to show this one, I would just, it's an AND, so they're in series, I got A and B, and the not B, I just show it like that. And then this one, I got two ORs. So I got this OR and this. B, and then I can just show the same thing again. Let's C, and D, and then I have my output Y. So there's some quick practice on how you would implement and or logic or and or not logic using relay contacts. So you'll see today when we get into the programming that the kind of programs you're going to write looks really close to this. But the meaning of these symbols will be slightly different, and we'll talk about those. So any questions over anything I just did? I think you should find that to be pretty easy. Well, let's jump into the PowerPoint, and if guys, I'll probably go over today, and I understand that some of you have classes probably right at 2, or you might have something you have to do. So what I'm going to do is I'm just going to keep going until I'm done with everything, and I'll post this. I'll post it like kind of like right away. When I say right away, I mean maybe tonight. I'll post it because I'm on campus up until like nighttime, so I won't probably later tonight or in the morning. But go back and watch the tail end of this before you attempt to do the lab. I'm going to say some stuff about the lab today and make a little bit more sense. So let's get into the PowerPoint. We have 2 PowerPoints. I have a document I want to show you, and if I have time, I'm going to go over the simulation software if I can figure out how to share. Well, I learned how to share a screen, but I got to make sure I can share an application. I haven't used that functionality before, but we'll see. So here we go. Here's programming the PLC. So as I mentioned, we use something called a ladder, electrical ladder to control devices. And it's much like the exercise we just did. The ladder looks just like that, only those symbols represent relay contacts that are normally open and normally closed. So when we program a PLC, it looks just like the electrical control ladder. So we call it relay ladder logic, or just a ladder for short. The language then is called ladder logic language, or a ladder logic diagram. And basically what that ladder logic diagram is a set of instructions. So this is a programming method where we don't use words, we use graphic symbols, and each symbol has a specific meaning. It's looking for a specific thing. So this is what we call a symbolic or graphical language. It's not like if you took C or C++, you actually write out English or write out your commands or instructions in English. Here we use a symbol, and the symbol has meaning. It's looking for certain things. So we use these symbols either in series or parallel to and to or, and the not things. We use this to make up what we call logic. And so they refer to this as contact symbology. It's graphical. There's 3 symbols. So now don't think of normally open and normally closed. When you see the next symbol, it's going to make you think of a normally open contact, but we're going to call it what it is. It's not normally open. These are the actual instructions. You still have normally open and normally closed switches. You still have normally open and normally closed contacts. But when you're programming, what we're using now, the instructions are not contacts. They make it look like contacts, so they kind of make sense to electricians, but they're actually instructions, and each instruction has a particular meaning and or it's looking for a particular thing that we'll talk about. So here's the first one. So this is the XIC instruction. If you look at it, the symbol for this instruction looks like kind of like a normally open contact. So this instruction, they say it's analogous to a normally open contact. It looks like it, but the IXC, this is called the examine if closed. Let me make this smaller. Okay, so when you think of this, examine if closed, that's the name of this. So in your mind, you think the IXC, but examine if closed is looking, actually has a specific meaning. So here's the way I want you to think about this. If you remember, we had the discussion about the input image table and the output image table. We had these discussions, and I'll refer to that in this PowerPoint. What those tables are, the input image table or output image table is just a bunch of registers. And you remember registers hold ones or zeros. And the cells in those registers are mapped to screw terminals that you can connect to the PLC, so you can connect your switches to it or whatever you're controlling. So let's say we have an input module with 16 switches on it, 16 screw positions. You can connect 16 buttons or 16 switches to those screw terminals. Then you would have a register inside of the memory of the PLC that has 16 spaces. And those registers are mapped to each screw terminal on the input module. And so if you screw, let's say you connect a button, a push button, to terminal number 2 on the input module. It's a normally open button. When you press that button down, then what happens is a signal is sent into the input module, and in that register that's mapped to that particular screw terminal, as long as that button is closed, there'll be a binary 1 in that cell in the register. When you release the button, there's a binary 0. So when you see these contacts named, the name says what they're looking for. So you got to remember, a closed switch is equivalent, a closed button or switch is equivalent to a binary 1. An open switch is equivalent to a binary 0. So the processor really doesn't know if the switch is open or closed. It doesn't look at the switches directly. What it's looking at is the registers in the input image table to see if there's a 1 or a 0 in a particular bit position. If there's a 1 there, then the processor knows whatever screw terminal is mapped to that cell, then that switch is closed. If there's a 0 there, the processor sees a 0, then it knows the switch mapped to that cell is open. So this command, this examine if closed, what are we examining? We're examining cells in the input image table to see if the switch is closed, but really we're saying we're examining a particular cell in the input image table to see if there's a 1 there. If there's a 1 there, then this command is going to be true. So the examine if closed command, instruction, is looking for a closed switch, or really is looking for a 1 in the bit position that this is mapped to of the input image table. So this command is looking for a 1. So here's a little bit more about the command. So we don't care what kind of input we have. It could be a button, it could be a switch, it could be whatever. It doesn't matter what kind of input we have. Whatever kind of input we have, we're always going to use this symbol to represent the input. We can use this symbol to represent a button, a switch, it doesn't matter. And each time you change the state of that button, it's going to change a bit in the input image table that's mapped to a particular cell. Now you got to remember what we said about digital devices. Typically a digital device, the smallest piece of information you can access is a byte. When you use your cell phone, when you use your computer, if you type the letter A or B, that letter A or B is stored. Now you know the code is called ASCII code. It's represented using 8 bits or 1 byte. When you move information around, you move around bytes or kilobytes or megabytes. You can't move around bits. PLCs are different. You can actually address a single bit, and that's what these commands do. This particular command examines a single bit in a register, and it is not word-oriented, it's bit-oriented. So, you know, the on and off, you know that now means if something's on, then we're storing a 1. If something is off, we're storing a 0. And so they call these status bits. And you can use the term, you know, 1, 0. You can use the term 1 or on or true. They all mean the same thing. The term 0 or off or false, all those words mean the same thing. And so here's what I was talking about. Here's 1 row out of the input image table. So imagine you have an input module, again, with 16 screw terminals that you can connect up to 16 buttons or 16 switches to those screw terminals. You can wire those directly to the screw terminals. what you see here, this is a register. This is actually a register, or you can think of it as a virtual logical structure. Think of these cells as existing in memory. Notice that they're labeled 0 all the way through 15. That's 16 cells that we have here. Each one of these cells can be mapped to a screw terminal on the input image table. So for instance, this particular one that we have in the example, this is the address. This is what the address looks like. So right here, this I says that this is a input. This is coming from the input module, and the address of the input module is input module number 12. So we have input module number 12, but this right here is the bit position in the register. And so if you go over here, this bit position in the register, if you give this address, then this bit position is affected by whatever screw terminal is mapped to that address. If that switch is open, then there's a 0 here. If that switch is closed, then there's a 1 here. And what this command is doing, this instruction, is looking at the, you told it by giving it this address, you told it to examine this bit position right there, and it's looking for a 1. If there's a 1 there, then this is true. If the switch is open and there's a 0 there, and they're showing you at the bottom, then it's false. So this examine if closed instruction is looking for a 1 in order to be true. If it sees a 0, then it's going to be false. Then you have this one. This kind of reminds you of a normally closed contact. It looks kind of like that on purpose so that plant electricians can understand it. But actually, this is the examine if open. The XIO, that stands for examine if open. And so it says it looks like a normally closed relay contact, but what this is looking for is an open switch. If I have an open switch connected to a screw terminal on the PLC, then in that bit position that is mapped to it, remember, a closed switch will store a 1, an open switch will store a 0. So if there's an open switch, whatever that terminal is mapped to in that cell, there's going to be a 0. This is actually looking for a 0. If this one sees a 0, it's going to be true. The examine if closed is looking for a 1 in order to be true. The examine if open instruction is looking for a 0 in order to be true. And so if we looked at this, just kind of jump down here to the register, here we have the examine if closed. There was when it was examine if closed, when there was a 1 there, this was true. Well, here we're using the examine if open. It's actually looking, that means there's an open switch out there connected to that PLC, so there's a 0 here. If it sees a 0 there, it knows there's an open switch, and this thing is going to be true. If the switch is closed, there's a 1 in the input image table, then this thing is going to be false. So this acts the opposite way compared to the examine if closed instruction. And so I have the same, you can go through here, kind of the same point-by-point description of this instruction. Again, it's a bit level instruction. It works on the on-off status, but I think the thing to remember is right here at the bottom. This is how it works. It's actually looking for this condition right here. It's looking for off condition. It's looking for the presence of a 0 in the cell in the input image table in order for this instruction to be true. So we have the examine if closed is looking for a 1 to be true. The examine if open is looking for a 0 in the input image table to be true. And then the last of the basic instructions is this one. We represent any output with the OTE, that's the output energize, instruction. And so what happens is, depending on the logic you write, if you have a rung and that rung is true all the way across, and we'll talk about what that means when it's true all the way across, but a continuous series of trues all the way across will set this particular instruction true. And if this instruction is true, whatever it maps to will turn on. It'll turn the light on, the motor, whatever you're controlling, it will turn it on. If this instruction is false, then it will turn off the device or not turn it on. So inside memory, here's what you have. You have a register, and now we have more. This is a program here. Here's a whole wrong program. This is a program. This is something like what you would write. So over here, we have the input module, and we got two switches or buttons connected to it. And these screw terminals here and screw terminals here, they're mapped to this bit position and mapped to this bit position. So when this button opens and closes, if it's closed, it's going to put a 1 in bit position 15. If it's open, it's going to put a 0 there. And then this cell, this button or switch is mapped to it. If it's closed, it's going to put a 1 in that bit position. If it's open, it's going to put a 0 in that bit position. So the last part of the address, is always the bit position in the register or in the image table. So since you wrote this program, you basically put two examine if closes. You put two of those instructions in series. So this right here is an AND circuit. You know, in order for AND to be true, both instructions have to be true. So what happens is when you run this program, then logic runs this way. This is going to examine this. If it sees a 1 there, then this is true. And then it moves over to here. It's going to examine this cell over here. If it sees a 1 there, this is going to be true. Since you're ANDing these, you have them in series, a true and the true and true is true. So now this is true. So now the bit position in the output, not the input, this bit position in the output image table, that bit is set to a 1. And when the processor scans that 1, whatever is mapped to this screw terminal in the output module, there's a motor, whatever's mapped to that is going to turn that thing on. It's going to turn on. Well, we can reverse the situation. Now, say the switches open up. So I have the switch open up. So now I have a 0 in this bit position. I have a 0 in this bit position. Now notice this one's still closed. Whatever was connected to the screw terminal 15 is still closed, so there's still a 1 there. But look what happens. This is going to look for a 1. It sees a 0 there, so this is false. This is looking for a 1. It sees a 1 over here, so this is true. But since you have these in series, they're ANDed together. When you AND a false and the true, if you AND those, you're going to get a false. So now when the PLC on the next scan is going to take this bit position in the output image table and change it to from a 1 to a 0. So now whatever's mapped to this particular screw terminal on the output module, that's going to be turned off. You use AND logic to turn it off. And so to review how these work, I have basically two sets of programs in this slide. So here we have a normally open push button connected to the input module. And so here's one cell. I showed you the whole row of in the register. This is one cell in the register or one cell in the input image table that this is mapped to. So I'm using the examine if close instruction. It's looking for a 1. It sees a 0, so it's false. But down here on the same program, I have it to look at switch A. It sees an open. It doesn't really look at the switch. It looks at the effect of the switch over here. So it's not looking at this. It knows what kind of switch is the position of the switch by looking at the status bit over here in that cell. Do I have a 0 there? If so, then the button is open. If I have a 1 there, then it's closed. And this is actually looking for an open button or a 0, so then this is true. So the logical values on the left side of this diagram should make perfect sense to you if you understand how the commands work. So now we close the push buttons over here. If I close that push button, then in that cell of the input image table that this is mapped to, there's a 1. So this is looking for a 1. It sees a 1 there, so it's true. This is looking for a 0. It sees a 1 there, so this one's false. So you want to mark this slide. This shows you the basic operation or the basic logical function of both the examine if open and the examine if close instruction. And so this, we can use these rungs to build either commands and instructions in series or instructions in parallel. We can use those examine if opens and examine if closes instructions to build more complicated programs. And as you basically each rung, each row is like the rung of a ladder. And so you build more and more complex control structures by building this ladder-like structure called a control ladder or ladder logic. And so there's some things here. I mean, you can read this yourself. I mean, we've already mentioned the term rung, so, just be familiar with that. What is a rung? It consists of input conditions which are based on the examine if open or examine if closed. There's a series of those connected in a series of parallel. And the last thing on each rung is going to be the output energized instruction, which represents an output. And each instruction has to have an address. The address does two things. It maps the screw terminal to the instruction and the instruction to a particular cell in the input image table. So the address is important. It's the link. It links the screw terminal to the command that you wrote, the examine if open or examine if closed, to the actual bit position in the input image table. Now, this term right here, and this is actually quite important, this term logic continuity. So there's electrical continuity, which means you have a continuous path through which current can flow. Electrical continuity means there's a continuous path through which current can flow. Logic continuity means there's a continuous set of true statements across a rung, and if all the inputs are true, whether we have examine if open or examine if closed, it doesn't matter. It's not the state of the switch being open and closed, it's the truth or falsity of the instruction. If I have a complete row of truths in a rung, then we say that we have logic continuity. The PLC works off of logic continuity and not current continuity. That's the point of your lab. Your lab is going to help you to understand what we mean by that. And so a whole rung is said to be true if it has a set of true statements leading up to the rightmost command, which is the output. Then the rung is true if all the previous input instructions are true, and if at least one is false, then the whole rung is false. So we have no logic continuity if I have a false rung. So this term logic continuity is quite important. So here's what the controller is doing. The processor determines the state of the on-off bits in the input image table. So what happens is, in the input image table, switches are opening and closing all the time. And so since that's happening, switches are opening and closing all the time, you have to update the input image table. And so what happens is the PLC program actually runs kind of in a circle, a scan, it's a circle. It'll look at the switches to see if they're open or closed. It'll take a snapshot of them. And then if a switch is open, it'll store 1. It'll store 0 in that bit position in the input image table in memory. If the switch is closed, it'll store 0 in that bit position in memory. And then it'll look at the program you wrote to see if you have examine if opens, examine if closed, and how they're connected with and or logic. And if you end up with a true rung, then it'll update the output image table and put a 1 there in that position that you have the output command mapped to. It'll put a 1 there. If you have a false rung, it'll put a 0 there. And in that way, we're able to implement any logical function. And so input instructions set up conditions under which the processor will make an output true or false. So ultimately, that's what you want to do. Use those input commands to give you a single true rung or a single false rung, which will then update the output image table with the 1 or 0 to turn the machine on or off. So you can read this. It talks about, we already kind of mentioned this, but if you find a continuous path of true, that's what we mean by logic continuity, then the output energized is true. If it finds a false rung, then the output energized will be false. You can kind of go through and read that yourself. Here, addressing is important. Addressing is the way as I mentioned, is the way we link the screw terminal to your instruction to a particular cell in the input image table. So as you go through your program, when you do your first lab, you're going to do like a tutorial first. When you go through that tutorial, you'll see, when you write the address and you connect it to a switch, and you'll see the position in the data table, the input image table, this will all come together and make sense to you. So addressing is important. You can read this slide. It talks about that some addresses are written in hex, some are written in octal. I think yours are in decimal. You are familiar now with all those number systems, so that shouldn't faze you. The particular simulation software you have is made to mimic the Allen Bradley SLC 500, SLC 500 PLC, and so they use decimal numbers they use decimal numbers for the bit positions 0 through 15, which makes it convenient. So here's how addressing works. Now what we're showing here in this diagram, what we're showing is a couple things. This is hardware. This is hardware. Everything in the middle here, this is all software. This is in memory. This is in memory, and this is the program down here that you wrote. That's all in memory. So you'll notice over here I got this switch connected to this screw terminal right here, and this is input module number 3. That's the address of the input module, and this is screw terminal number 12. So in the table, when this switch is, you've mapped it to that 12th cell. Was actually the 13th because you start counting by 0, but this is cell number 12 right here. So you've mapped that. You use this address. Here's the command here's the instructions you wrote at the bottom. You said use input module 3, bit position 12. So now you've mapped this screw terminal to that cell, and then this command right here is going to look at that cell that you mapped it to. And since you use the examine if closed, it's looking to see whether that's a 1 or a 0. If it's a 1, then this is going to be true. If that's a 0, that's going to be false. So when this is closed, there's a 1 there. This is true. And since this is true, that makes this whole rung true. So now that makes this true. This is the output command. It's true. So in the output image table, in that bit position, since that rung is true, it's going to put a 1 there. And when the PLC scans back around and sees a 1 there, then whatever screw terminal that's mapped to, which is this one, is going to turn that device on. If you open this switch up, then there's a 0 here. Next time it scans around and sees a 0 there, it's going to look at this, actually here. It's going to see a 0 here. If you open this switch up, it's going to see a 0 there. This is going to change from a true to a false, and that's going to change this to false. And this when it updates, this is now going to be a 0. And when it scans back around, it's going to turn this device off. So you have full control over whether this is off or on by putting 1s and 0s here in the output image table. And whether you get a 1 there in the output image table depends on the logic that you write down here. So the address is vital. It's the link between the screw terminal, the command that you wrote, and the cell position in the row in the input image table or the register. Vitally important. I'm not going to talk about connection diagrams. You guys can look at this if you want. I won't say anything about that. Let's talk about branches. So you already know that if I have a branch, branches represent ORs. So here's a simple OR, simple branch instruction. But I can also have something called a nested branch. I can have something that looks like this. So a nested branch, I have a branch within a branch. Here's a branch. That branch is within a bigger branch. So that's called a nested branch. And some PLCs, there's no way to implement this. So what you do is you can do this. These two circuits are logically equivalent. So if you have this, you can't, in your software, there's no way to implement this inner branch. So you can do this. This is equivalent to what's above. So I would just say mark this and remember these two are logically equivalent. Now, most PLCs have a memory for internal storage bits. So these are called internal bits, or if you have an internal relay contact. So an internal contact is a contact that does not access anything outside the PLC. It's not connected to any button or switch. It's all internal. So it's just a 1 or 0 that can act like an internal switch. And so they call that an internal control relay or internal contact. Now there's a lot of things you can do with that, but let me just show you one right here. They mentioned this. You can read this. This gives you a little bit better understanding of internal relay or internal contact. I think this part right here kind of defines what it is, and here's some of the reasons why you want to have it. But let me just show you what you can do with it. So here are 2 rungs. Here are 2 rungs. So this is looks like I should have started this with 0, but I started with 1. So here I have these 8 commands, and let's say I couldn't get any more instructions on this row. I couldn't get any more instructions on this rung, but I need more instructions. I need my ladder rung to be longer. What I can do is this right here says it's an internal relay coil, which means this is not even mapped to the output image table. What you're going to do is, now imagine that this right here is the address. This right here is the address. That's the internal relay coil. That's the address. Notice I've given this command the address of this output right here. These 2 have the same address. So here's what happens. If I have logic continuity across here, that means all these contacts are true, and that's going to turn this internal relay contact on, which means it's true. So somewhere in a table or in memory, there's going to be a 1 stored to represent the true state of this. Now, since this is true, and this is the examine if closed, it's looking for a true. Since that's true, now this is going to be true. So basically what you're doing is you're using this output command. Let me clean this up. You're using this output command right here to extend the length of that rung. So now all of these rungs, this is kind of tied together between, let me get rid of this. It's tied together. These 2 commands make this one long rung right here. So one thing I can use an internal contact for is to, if I need to have a continuous or longer rung, I can just give this instruction the address of this output, and basically it has the effect of extending that rung. I can have more inputs on that rung. There are other reasons why you wouldn't use an internal contact, but that's one I think most students could wrap their minds around. Now, this slide right here, this next one is really important. Now, guys, remember, I got about 10 minutes. I'm going to keep talking and go through this. You just guys are going to have to go back and watch the video because I still have another PowerPoint to go through, and I want to talk about the simulation software. So if you have to sign off at 2 o'clock, that's fine. Just please come back. I'll try to post this video to YouTube. I'll post it tonight, and you can go back and watch it before you do your lab. So what you have at the top here is a hardwired circuit. You can see how this is going to work. I have a push button, normally open. I have another push button, normally closed, and I have a pilot light. So don't worry about electrically how it works. I mean, logically, you can see what's going to happen. You can see real easy that nothing's going to happen to this light right here until I push this button. When I push this button, current can now flow through here. Since this is normally closed, it can flow through here, and that pilot light's going to light up. So what kind of logic do I need to implement this? Well, you might think to yourself, if you did a direct translation of this symbol, here's what you would do. This would translate as a normally open contact, and this would translate as a normally closed contact. But if you did that button by button translation, then this would be the wrong, it's the correct electrical translation, but not the correct logical translation. The PLC works off logic continuity. So in order for the PLC, in order to implement this in the PLC, it needs for this to be true and for this to be true. Well, this is already true because it's closed. That's already a 1. right? So this right here, when it looks at that normally closed button, it's already a 1. It's already a true. So this is already true. As soon as you implement this, it's already true. So this right here is going to look at that. And when that button is pushed, then this will become true. And since you've ANDed these together, this will become true. So even though you might at first glance think, well, this is normally closed, I need to make that a normally closed contact, that would be incorrect. That's not how it functions. It looks like electrically how you would do it, but logically, that's not how the circuit functions. So in order to get this to function, you will need 2 examine if closed contacts ANDed together to get this to operate logically, the way it's designed to work logically. That's what we mean by logic continuity. Here's another example. So notice in these examples, you got to understand how the hardwire circuit works in order to implement it in logic. So here's the description over here. It says when the push button is open, when this push button is open, the relay contact is de-energized. That means it's off. And the contact CR1 will close to turn on the pilot. So here's what we have. Let me get off the camera for a second. I want to go to the camera. I want to make sure you understand this. So remember when we have a relay, I showed you the relay. You had a relay coil, and you had the part that moves, and then you had a contact right here. If I put a power source down here, if I close this circuit down here, then this contact will close. If I remove power, then that contact will open. So that right there, that's a normally open contact, a normally open contact. So I would show that like this. This is a normally open relay contact. Well, remember what I said, when we have this relay, there's no reason why I can't take another contact and put right there. This one right here will touch that armature when the relay is off. So this is the normally closed contact. It looks like this. Normally closed contact looks like that. So in that circuit, that diagram I showed you, instead of having the, whatever we're controlling, the pilot light controlled by this, the pilot light is hooked to the normally closed contact. So if you turn this on, you'd actually be turning the pilot light off. So you got to look at what you're dealing with in order to understand what kind of logic to use to control the circuit. So we're using the normally closed. So we actually want, when this thing is off, the pilot light to turn on. So that's important that you understand how the relay works. Now, if you understand that, let's go back to the PowerPoint and look at the logic that we use to represent that. I gotta find that diagram. So look at this logic, guys. Look at it. Let me find it. Okay. So now, if you understand what I just said, you got the push button, it's open. So if this is open, that means no power is getting to that contact. That means that the relay's off, so that armature is touching that top contact I just showed you on the whiteboard. It's touching the normally closed contact. And that, if you were to push this button, that would turn the relay on, and the magnet will pull it down and disconnect it from the circuit. It'll go down to the normally open contact, and it'll close it. So if I want to implement this, the way this works, it says that when this is open, when this button, I'm sorry, when this is open, then this relay is off, but since we're using the normally closed contact, it's going to turn the pilot light on. When you energize the relay, it actually turns the pilot light off. So how will I implement that in logic? Well, this thing right here is looking at that button right there. It's not looking at this, it's looking at that button right there. And remember, if that button is open, then there's a 0 there, or false. That button is closed, there's a 1 there. Well, since that's open, this is actually looking for a 0. Since it sees an open switch, examine if open. It sees a 0 there, that makes this true, which will make this true. So this simple logic circuit implements the control of these two rungs in the actual electrical circuit. So again, that term logic continuity is really, really important. So mark this slide. You know, this will come at you. You gotta, and by the time you get done with lab 1, you'll understand what we mean by logic continuity if you don't understand it already. So you can read this slide. These are some of the modes of operations. PLCs, they'll have some of these. They could have all of them. Usually it's some combination of them. You can read this. I'm not going to waste time on this. And so that's the end of this one. So it's almost 2 o'clock. So I see I'm going to go over. I'm going to still keep going because you need the information for your lab. So I'm going to keep going. I don't know how long this is going to go. So you 2 o'clockers, the people that's got to leave at 2, go right ahead and leave. I'm going to go through the next PowerPoint, which is not quite as long as this one. Well, I don't think. We'll go through the next PowerPoint because it talks about, now that we kind of got a flavor for how the programming works, what's going on in memory. To really understand the program well, you got to know what's going on in memory with the program. So that'll talk about that. And then what I want to do is I want to go over the lab 1. I want to talk about a really, really I don't know what a common circuit you use to control devices, and your lab is based on that. And then if I can get the simulator to share, I just want to go through the simulation. So if you got to leave at 2, what I'll do when I get home, I got a night class tonight, so I'll try to get it up tonight, guys. I'll try to put it up on Blackboard on YouTube, but sometimes I'm so tired. But I promise you, by the morning, I'll have the video up there. Watch the video, the end of it, before you try the lab, because I want to explain some stuff about the circuit that you're going to design in your lab 1. Okay, so I'm going to keep going. If you got to sign off, go right ahead and sign off. I'm going to go to the next PowerPoint. All right, so this next PowerPoint, programming memory. What does that program, what's going on in memory with that program? And again, you don't have to know this to program, but you'll really understand your programming a lot better if you know what's going on in memory. So just kind of a summary. Now this really is designed to be done the day from now. We're doing 2 slides in 1 day. So this is kind of an overview right here. This we got from the last PowerPoint. So it says each input and output of the PLC module terminal is identified by a unique address. You know that already. Each screw terminal on the input module and each screw terminal on the output module has a unique address. The symbol for input is a cat. So you can use the examinative open or examinative close. They look like relay contacts. So any kind of input, doesn't matter what it is, we're going to use one of those symbols to represent it. And then the output, no matter what you're controlling, it could be a light, a heater, a motor, any output, we're going to represent that in the PLC program as a relay coil. So with that in mind, let's talk about memory organization. How is memory organized? So when you deal with digital devices that have memory, the term memory map comes up. A memory map. And all a memory map does, it just says how a memory is located, how it's divided up. So and here I have 2 memory maps. I'm going to show you quickly. Here's one memory map, and here's another memory map. So basically, this memory map is for the PLC-2, Allen Bradley PLC-2, and it divides memory. Memory isn't really divided like this. This just gives you a logical way to think about memory. So for this particular model PLC, these are the addresses in memory for these sections of memory. Okay, so like the counter timer accumulation values are in this section of memory. So there's reasons why you would want to know that. Now, you don't really need to know this. This is a more detailed memory map, but the one I want you to know for like the exam is this. All PLCs have a memory map. They're not all organized like this. I mean, this detailed organization depends on who makes the PLC, the manufacturer. But you can think of any PLC memory map of looking like this. All PLCs would have a memory map that consists of these three pieces. So this is the one I want you to remember for exams, quizzes, and just as you go through and use the program. So there's three sections of memory in any PLC. There's going to be the data table section. Now, data table and input-output image table mean the same thing. In your book, they call it the data input-output image table. In the actual PLC, when you buy one, they'll call it the data table. So they mean the same. So in memory, there's a section for the data table. There's a section for the program that you write, the user program. And then this part of memory we call housekeeping. That's for the part, you don't have any access to that. That runs the background, stuff in the background that you don't realize is happening. That part of memory takes control of all of that. So this memory map is important. This is kind of a general memory map. It says for the Allen Bradley PLC-2, but any PLC will have this general memory map. So let's dig into each section. So what this does is we're going to look at each of the three sections we talked about. Well, at least two of the three. So the first part is the user program section. That's the part you write a program using those commands that we just talked about, examine if open, examine if closed commands, instructions. And you got to store that program somewhere when you run it. Well, it's stored in the user section of memory. And so you can read this. I'm not going to read it to you, but basically just know it's where your program is stored. I want this right. Okay. So it's where your ladder is kept. And it also says here that this will account for most of the memory of the PLC. So if you have a really, really long program, most of the memory, the kilobytes, whatever minute number of kilobytes, most of them will be used right here. Okay, so it says most instructions require 1 word of memory. Well, a single switch only requires 1 bit, but we'll get into more complicated output devices like counters and timers, and they actually require at least 1 word or more. So you end up using a lot of those cells in your memory. So the user program section is where your program is, and that accounts for most of memory usage. Then there's the data table. Those are the input-output image tables that we've been talking about, and all they do is store zeros and ones. In the input image table, it's going to store zeros and ones, and those zeros and ones are going to indicate if the switches mapped to the cells are open or closed. In the output image table, it's going to store zeros and ones, and those zeros and ones are going to represent how many of the rungs are true, how many are false. If you have logic continuity for a particular rung, then that bit position mapped to that output command is going to store a 1. If you have a false rung or no logic continuity, there's going to be 0 stored there. So usually they have something called a processor file, and this is just kind of a logical, there's really no processor file. This is just a logical way of organizing input outputs. So you have what they call program file and data file. So if you were to store and save these, your program will be stored in a program file, and then you have data, which basically your data here so far is going to be input, output, image table. They're going to be stored in the data file. So it's just a way to organize. And so you can think of it like this. You got your hardware over here. You got your switch connected up to this screw terminal. This right here is really a row in the input image table, but you can think of this as a file, as a data file. This is the data files. So that switch is closed. There's a 1 there. So in the input image table in that data file, there's going to be a 1 stored there. Here you have other data files because you have other programs you might have stored, and the data for all those can be stored in other files. I don't know what happens when I make this go blue like that. Guys, I'm gonna have to hold on a second. I'm gonna have to I don't know what happens when this happens. I get off of this. I'm gonna click off of this. and then go back. When it turns blue like that, I can't turn it back to what it needs to be for some reason. Okay, so this is showing now the output image table right here. So I got the output image table still in the data file. It's since there in that previous slide, since there was a 1 there, that rung is has logic continuity. So when it updates, it's going to update this cell in the output image table to a 1, which is going to turn this light on. So the point of this is you can think of these output image tables and input image tables as being kind of files. This is just for organization. Just the way to think of how data is organized. Now this slide is important to understanding how the PLC works. What you got to remember is a PLC works in like a loop. It's not like a regular program where you start the program, you go through some steps, and then you end it. There is no ending the program. What the PLC will do is it'll continuously read that ladder up and down. It continuously runs in a loop. So here's the parts of the loop. There's 2 parts of the loop. There's this top part, the I/O scan, where it scans it scans the state of the switches, and then there's the program scan where you tell it what to do with the 1s and 0s that result from the state of those switches. And so what you want to remember from this slide, and you want to write this down, is this equation right here. So this is called an operating cycle. It consists of a program scan, and we're going to scan the I/O, input-output scan. A program scan, and the input-output scan. So we kind of break it down here. So the I/O scan records the status of data of the input devices. So those switches open or close. If they're open, there's going to be a 0 stored. If they're closed, there's going to be 1 stored for each individual button or switch. The program scan scans the program that you write to see what to do with those 0s or 1s. So this kind of breaks it down in words. So I would mark the previous slide and then this one. The PLC will first read all inputs. It's going to check the state of the switches, the sensors, to see if it should store a 1 or a 0. It's going to put the appropriate binary value in the input image table, the data table. And then it's going to look at the program that you work to see how to respond to those 1s or 0s. What we're trying to get is logic continuity. If there's logic continuity, it's going to update the output table, which will either energize or de-energize whatever those cells are mapped to in the output image table or on the output module. And that's this last part. So here's kind of in words, and here's another picture of it. You got to remember the PLC works in a loop. So it's this scan process. It's going to read inputs, run the program, adjust outputs. Read inputs, run program, adjust outputs. So it goes around this loop continuously until you turn the machine off. So here we go. Here's the scan process. So what you got to remember is everything right here is software. This is inside the PLC. So you got here's the memory, the user memory where you have your program, and here's the data memory where the input-output image table is stored. And everything on the left side and the right side, this is all hardware. So how does this work? Well, you have this push button connected to this screw terminal, and you've given it this address. When you give it this address, you've automatically picked out input module number 3, bit position number 6 in the data table. And since you've given that address, this is going to look at that bit position in the data table. So it's looking at that bit position in the input image table. If this rung is true, then it's going to update the output image table with a 1. If this rung is false, it's going to update the output image table with a 0. And then when it comes around in that scan, whatever this is mapped to, whatever screw terminal this is mapped to, if this is true, it's going to turn this device on. If this is false, it's going to turn that device off. So you have full control over whether this thing over here is on or off by the logic you write down here and the combination of input and outputs that's done over here. So we'll just kind of run through this. We run through here, and then you just kind of watch up here in the red. It kind of walks you through here. So I'll just click on this and you can read it. So we started here, and we go here. This is closed. So when it scans, since that's closed, this bit position is going to, it's a 1 now. Then we go here. Oh, let me go back. So that's a 1, which makes, since you have this mapped to that, and that's a 1, that makes this rung true. Then we go here. Since that's true, this is true. And since that's true, it's going to turn this light on. So now I'm going to click through again. We have a 0 here now. Now notice this is still on because now we're doing another scan. So this is on at the moment. But now watch right here. This is true. And then when this turns to a 0, because this rung now has no logic continuity, it's going to turn that off. So when you go back and review these slides, if you just kind of start right here, and then just kind of click through these and just kind of follow and understand what's going on. If you understand what's going on through these slides, then you'll understand what's going on in memory of the PLC. Okay, so I think that's a good way to review that. So this idea of scan time, so this time, so it takes time for each instruction to be executed. So the amount of time depends on the instructions you use, how many you use. Right here, it takes less time for a processor to read an input that's either open or closed than it does to read the input of a counter. So it takes time. This idea of time is important. We'll talk about why it's important in just a second. I don't really care about this scan pattern slide. Basically, in your PLC, here's your ladder. Your processor is going to read from that, start at the upper. It's going to start at the, if this is your ladder, it's going to start right here at the upper rung in the left. It's going to read across here, then come back and read the next rung, then come back and read the next rung, and come back and read the next rung. It's what we call a horizontal scan pattern. So don't worry about this over here. I don't care about that. This is showing you a picture of the scan pattern. So yours kind of works like this, the way it reads your actual program. Now this slide right here is important. So take a second and read this. Just read this to yourself. All right, so hopefully you can understand the importance of a thing called scan time. So let me just, I hate to read the PowerPoint, but let me just read to emphasize certain things. How fast a controller can react to changes in the input. That's what we mean by PLC scan time. How fast the controller can react to changes in the input. Scan time varies with program content and length. That should make sense to you. The more instructions you have on a rung, and the more rungs you have in the program, the longer it's going to take the PLC to scan. The more switches you have hooked to an input module, the more it has to keep track of in the input image table, the longer it's going to take to scan. And so scan time is important because if there's something, imagine this. If let's say, well, here's an example here. It says if it takes 8 milliseconds for the CPU to scan a program. If it takes 8 milliseconds for the scan to go through, to look at the switches, to update the input image table, to look at your program, and to update the output image table, if it takes 8 milliseconds for that, but you have a contact of a switch opening and closing every 4 milliseconds, you can see some of the information is going to be missed. The scan time has to be faster than the frequency of any switch opening and closing. Theoretically, it needs to be twice as fast. But you can see if you run into trouble if you have something in the field happening faster than the scan time. Now, typically, with mechanical switches, you don't have to really worry about this, but just be aware that that could be a potential issue. If you have something that's really, really, really high speed and it's faster than the scan time of your PLC, then it can be an issue. So mark this slide and understand what I mean by scan time and know what kind of problems can arise, or know when it can be a problem. It can be a problem if you have some device with a frequency of something happening faster than the scan time of the PLC. Data can be missed. All right, so that does it for the PowerPoint. Does anybody have any questions over either of the two PowerPoints that I went through? Okay, well, this document right here, I'm not gonna, you can read, this is on your Canvas. You can read this yourself. It just talks about entering ladder logic. I'm not gonna quiz you or test you over it. This is just for your own information. You just kind of read that. Now, I want to go into one thing. I want to talk about something that's really, really important, and this is going to help you with your first program. So when I want to start a machine, a really, really heavy machine, by now you understand there's different kind of buttons, there's different kind of switches, there's all kind of stuff that we can use. I can use a big lever switch. If I want to say I have a big 50 horsepower electric motor, maybe for an elevator. I can use a big knife switch to turn it off and on if I want to. But that's not the safest way to do it. Typically, we don't want a switch that is going to stay on or stay off. The normal way of starting and stopping switches is using something called a latch. And I want to attempt to explain the way a latch works, the logic of the latch. And again, your first lab deals with this. So this latch is called a latch or seal-in circuit. So let me just try to walk through this and help you to see the logic of this. Okay, so here's how this would work. So I would have a button that I can push, right? And then over here, I have a relay contact. So I'm going to make the relay contact a circle. So there's a relay contact. This is a relay coil, so I'll just put coil. We'll say CR1. So control relay 1. So I push this button. Let's just call that button A. I push that button down, and then whatever I have down here, I can control that. I can turn this thing on by pushing that button down, as long as, this thing right here is looking at that. When I push that down, this relay comes on, right? This relay energizes and closes the contact, which turns this on. Well, this is a normally closed button, a normally open button, so it's only going to activate this while I have it pushed down. When I open that back up, then it's going to interrupt power to this. It's going to turn this off. What I want to do is have a start button. This is a start-stop circuit. That's what this seal-in stuff is about. But I want to do it. I don't want to have a continuous button that's closed all the time. What if it fails in the closed position? You can't turn it off. So this is the safest way to start or stop big machines. So it works like this. I'm going to show you the logic of it.
So is this like a push to start engine on like a car?
Yes.
Okay.
Yes. Yes. Good example. So what you have is well, let me see, how do I want to show this? I'm going to kind of combine logic and the switches here. I hope this isn't confusing. I'm trying to see the best way to talk about it. So if I push this button right here, as I said before, this is on, but since this is a normally open push button, when I release it, then this turns off. It's like a doorbell. But what you're going to do is you're going to have another contact right here. You'll have a contact right here. And that contact, you give it the address of this. So you give it the address of this. So let's say the address, I don't know, I'm just going to call it, I'll just use the CR. So here's the address of this. So I have this push button, I have this relay. So you can see how that works. Without this, I push that button down, the relay is on. When I release it, since it acts like a doorbell, this is off. All you're going to do is add this. You're going to OR a contact with this button. You're going to OR it like that. So now you have an OR. So if this is pushed, then I have flow through here, turn that on. This has no way to close though, because what I'm going to do is I'm going to give this contact the address of this relay coil. So this contact only closes when that relay is energized. So let me step through it and watch what happens. Without this, I push this down, this is on, I release it, this is off. With this, I push this down, and current, since this is an OR circuit, current now can flow through here, and it can also flow through here. When I let this go and turn this switch off, relay, since this is true now, current now has a path through here. This is an OR, so either one of these have to be true, right? This is false now, but that's still true, so this thing stays on, it's latched. This right here, when we use the term seal-in, this is actually the actual seal-in contact. That's the seal-in contact. So that thing is locked on. Now stuck on, there's no way to turn it off. So typically when you do this, you'll have this. You'll have your push button, and you have the thing that you're controlling, your coil. You OR this with the contact, and the key to this circuit is you have to give this command the same address as that. That's what latches. That makes it a latch. So you got to give this the same address. This address and that address have to match. But then there's no way to turn it off. So then what you'll have over here, you'll have a normally closed button over here that you can use to interrupt that. So when this is up, there's no way for this to turn on. So you push this down, you push that down, there's now a path. There's logic continuity through there. There's a path for current to flow through here, which closes this relay. So now there's a path through here. And if this gets current, it doesn't matter if the current's coming from that rung or this one. If this is getting current, it's going to stay on. So now when you open this back up, the current stops from that top path, but it still has a current feed from the bottom. So now you got to have a way to turn it off. So to turn it off, you have to use a interrupt here. You can interrupt that button, and disconnect it. Let me show you this in the simulator. This will be a little bit better, I think, for you to understand.
Wait, can you put the normally close push button on the second rung, not on the first one, so that way, like, when you turn it off, it'll interrupt it?
Yeah, that's where you would put it, but I want to show you,
Okay.
it's a little better in the simulator. That's exactly where you would put it. Let me show you on the simulator. Now, guys, can you, wait a minute. Okay, hold on a second. I got to figure out how to share. Hold on. Be patient with me because I've never. Share files. Share application. Okay. All right, so I think I want to share. Let me know if this works. Can you see this?
Yep.
Okay. All right, so let's just, I don't know if you had a chance to look at this or not yet, but this guy right here, you can just get rid of him. I just get rid of that because it's kind of annoying. But so what you have here is you got just kind of the layout of this. Up here is just like your regular Microsoft product. So you got your file, you can create a new program, save, you can save rungs as picture. Now the print, I don't think you can use that in the free trial. I'm pretty sure you can't. There's something you can't use. I can't remember. I'm sure when you guys download it, you'll be able to determine that. So right here, this screen is divided up in the two windows, and right now it's set up to edit. This is the edit window over here. This is the edit window, and I can X off of this over here, and when I do that, watch what happens. You see these files over here. This actually is kind of important here. So remember we talked about in the PowerPoint, there's data files and there's program files. So this is kind of organized in that file structure. You see data files here, and you see program files here. So if you were to actually do a program and you were to save it, you can open this up and you see your ladders in here. Okay, so these are your ladders. Don't worry about this. These are subroutines, but your main ladders will be stored here, and then your data will be stored over here. So you have these different tables. You have an output table. This output table is the output image table. Here's the input image table. These are status bits. These are all, this will make sense as we go through the course. Your output, input are important, and your counter and timer tables are important, but I'll show you that here in a second. So, but the other thing, when you X out of this, you can go over to here, simulations, and look at all these simulators we have. There is a I/O simulator. So right here, if I press that, then you have your input-output modules. If you open the screen up all the way, you see some thumb wheels there. But now we talked about the physical PLC. We talked about the PLC. Here we have an input module. Notice the I:. So the way this address schema works, you have I:1, and then you have this is an O, not a 0. So this stands for input module 1, output module 2, input module 3, output module 4. So that you think of these in pairs. The odd numbers are my input modules, and the even numbers are my output modules. The other thing to notice is that I have these switches over here. You see, I have this starts at 0 and goes all the way to 15. So these represent those screw terminals that I talk about. And they're just showing you they already got the switches pre-wired for you. So this represents hardware in your simulator. This is hardware, and for each screw terminal, there's an LED right here. And that LED just lets you know whether a switch is on or off. See, if I click that, this thing lights up red, I know it's on. And then I'll see the same thing over here when I have an output that's on. So I can turn the switch on or off. I'm just clicking my right mouse button right now. So even I can just see that that's because it's red, the LED is on, and that's off. Now I'm going to right click this. Watch what happens when I right click. If I right click it, I can change the type of switch I have. So I can change this. If I right click it, now that is you can hover over it, it'll tell you that it says left click to maintain, right click. If I left click this is a normally open push button. I'm going to click my left mouse button and watch what happens. See that? As I click my button, it opens. I can right click it again. I can change it to a normally closed push button and have the opposite effect. So I have these choices. I have this one. That's a limit switch. I have that one. There's a normally open, normally closed buttons. So I'm just right clicking that to get the different buttons. So you got a few options there. Up here is your instruction set. And so the main one is going to be this first one. If I just point to that and just hover over it, it just tells you what these instructions are. Okay, so right now I'm on this user tab. And so the instructions I have in that user tab, I got the new rung, I got a branch, I got your examine if close, I got your examine if open, I got the output energize, I got the latches here, an output latch, latch and unlatch, and I can scroll this over right here. I can click these other tabs to get other parts of the instruction set, and I have a scroll bar here. I can scroll over. You have quite a bit of instructions here. So we'll deal with some of these, some we won't. I would just get in here and play around with this stuff if you want to become more familiar with it. But most of the time you'll be on this user tab. If I want to change to another simulator, I got a traffic simulator here. You actually use this for one of your labs. So I got the traffic simulator. Just kind of play around with this. I got a bottle factory here. I can use a conveyor to make these bottles. So I have different things that I can do. Most of the time you're going to be here. You want your I/O simulation. So what you want to do here is you'll edit. In your edit window, I'm going to go back to my user instructions, and I want to add a rung. When you start a program, a lot of times you can go over here and just, if you want to clear out the memory and the data tables, go here to new and just hit that. And then you don't have to worry about any of this stuff. Just say OK, and it'll clear out your program for you. But it erases everything in the data table. It won't store anything. So once you do that, you'll always have this rung right here. This is the end rung. That's like the end to the program. You might write an end statement in a program. So here's the end, the way we end the ladder rung. This is here automatically. You can add a rung by just clicking on that. I'll click one time. Now once I add a rung, I can start adding these commands to it. So let's say I want to make a simple AND circuit. Well, you know, an AND is going to be two contacts in series. So I'm just going to, now what I'm doing, you can either double click on it, on the command, or you can just left click on it and drag it. I find that when you double click, you have less control. Sometimes the commands go where they want to. So I like to just click on it and just drag it. You can just experiment with your machine. I think the environment that you have this program running in makes a difference. So it just depends. But I'm just going to left click on this, and I'm going to drag it over. And when I drag it, you'll see that this turns red. I can release it, and it'll snap to the rung. It'll snap to the rung. So I want to make an AND circuit. So I'm going to drag another one over and snaps to the rung. Now, this is my output. Don't use these latches right now. I mean, you can cheat and use those, but if you just use this input, since that's an output, remember the output is always the rightmost command on the rung. So no matter where I put this, it's going to snap over to the right. So if I move this over here and drop it, you see it snaps over here to the right. Now notice these have question marks on them. And the question mark is they want to know, well, what's the address? You got to map this to a screw terminal over here. So you have a choice. You can double click on that, and you can actually type the address. You can type 1:, I mean, this is an I, not a 1. I :1/00. You can type that if you want to. Just by the way, when you hit the colon on your keyboard, you got to use your shift key, right? You hit shift colon to get the 2 dots. With this program, you can actually do a semi. They have it set up to where you can enter a semicolon, so you don't have to hit that shift key. It'll change it to a colon automatically. It just saves you a keystroke. But that's not how I usually do it. What I usually do is you can just actually come over here to the address you want and left click on it and just drag it over here and just drop it. So you never really have to type an address unless you want to. So now what I've done is I mapped this instruction to that switch, and I'm going to map this switch to this instruction. I'm just going to drop the address there. Now, anytime you write a program, commenting is important. You want to label things. You want to comment to say what things do. You can never have too many comments. Well, you can comment an instruction or you can comment a whole wrong. Let me give this an address. This output wants an address. We'll just we'll map it to this one right here. So output module 2, screw terminal 00 or bit position 00. So I'm going to drag that over here and just drop it. Now what you can do is I'm going to right click on this. When I right click on it, you have these options. I can cut. If you want to delete it, you would just cut it. I can copy it. I can paste left, paste right to where I am. But what I want you to focus on is this one. With that edit, I'm able to label this. We can call this switch, I don't know, let's just call it switch A and switch B. So you always want to try to label when you want. So this will be switch B. As you get into more detailed programs, this will be important. You can also, if you want to, come in here and you can change the state of this. Here we have examine if close. I can change it to examine if open if I want, by just toggling that there if you don't want to type in a new one. And then here, I don't know what to call this. We'll just call it light. Maybe this is some kind of a light. So you can comment each individual instruction. You can also click over here on the wrong number, and I can right click on that, and you can actually comment a whole wrong. I'm not going to do it because it's going to get in our way, but you can click on that and you can give this wrong. And that's a good thing to do, is to get in there and write down wrong for wrong what the wrongs are doing. If you have a short program, it's not going to make a difference. When we get into long programs, it's going to make a difference. You want to comment, label each instruction and label your wrongs. Now, once you've done that, you can, see, I can close this and I can close this, but over here nothing happens because you're still in the edit window. You're editing this. You want to run this now. So in order to run it, remember when we were talking earlier, when we talked about the PLC programming device actually having memory? Typically what you do with a PLC, you'll program it in a handheld programmer or maybe even a PC. You'll program it, and then you got to move the program from the programming device to the actual PLC. And once you move the software to the PLC, your program, you can actually unplug the programming device if you want to. Well, that's called downloading the program. So there's a button. What you'll do is this toggle, this is the PLC panel, and I can toggle this over here, and I can go to, this is my edit, and I can go to my PLC control. So I'm just clicking on that, and I can toggle from my instruction set to the actual PLC control. So what I want to do is I want to download this, and this mimics moving the program from the programming device to the actual CPU of the PLC. And at that point, you can unplug the programming device. So let me go ahead and download it, and now download it. So now what happens, now watch over here, when I close switch 1, this one, when I close that, nothing still happens. Now why doesn't anything happen? Well, I've downloaded it, I've actually moved it to the CPU, but what I forgot to do is over here, I got to set the PLC to the run position. Remember we said we had the different modes, and I said that some PLCs will have all these modes. You have some combination of the modes. Well, practically all PLCs will have a program mode and a run mode, and this one actually has a step mode, and there's other mode, edit modes, remote run. The only one you got to concern yourself with is the program mode and the run mode. So right now, even though I've downloaded it, I'm still in program mode. I got to change it to run mode, and that's done on purpose because you don't want to accidentally run a program when you're trying to edit it. You don't want, especially if you're connected to an actual factory a process, you don't want to accidentally run something. So this is done on purpose. So now when I change this to run mode, now when I close the switch, watch what happens. I'm going to close this switch, and you can see that this lights up bright yellow, indicating that that command is true. It's on. It's true. That's a logical true. Well, this is, since I have these in series, a logical true and another logical true should make the output over here true. When I close this, you see this turns yellow. So now I have logic continuity over here, and you can see that this is true now. If I make either one of these false by opening it up, you see that this turns off. Also look at the light. There's a little LED light here on the output module that I have this mapped to, indicating that this is on. So this run right here is, as logic continuity through it, is logically true. Now, if I open these up, now remember we talked about the input and output image table, the input-output image table. Well, in the PLC, that's called the data table. You'll see up here there's a set of tools. You have this, you can decrease the font, you can increase the font, but right here, the tool, when you point to that, it brings up the data table. So this is what, when we refer to in the slides, the input-output image table, when we refer to that, we're really talking about the data table. Okay, so if I open that up, let's take a look at the data table. So now this is actually running in real time. Which data table are we looking at? This is the output data table. So this is going to show the state of the outputs, and I can, down here, I can change the table. Look at all these. Oh, hold on a second, I lost my lights. I'm in a room with automatic lights, and the lights go off by themselves. So I can change to the input image table, and basically for everything we had over here, for all of these files, wait a minute, for all of these files over here, all these files on this side, there's a table for each one of these. Now the one you have to concern yourself with is the output table, the input table, the counter table, and the timer table. Those are the ones that we're going to deal with. But let me just show you something real quick here. So in real time, this right here, these are the addresses of the modules. This is, let me get rid of this. So right here, this is output module 0. This is output module 1. We don't have an output module 0, so there's nothing here in this row. But right here, notice there's a row, and these little circles are really zeros. So I don't have anything here because I don't have a module that's called input module 0 or input module 2. I do have an input module 1 and the input module 3, and I'm using input module 1 right now, and I'm mapped to this bit position over here. I got a switch. I'm using 0, 0, and I'm using 0, 1 on the input. Now watch what happens when I close this. I'm going to close input module 1, bit position 0, 0. If I close this switch, and then I look over here in the table, there's a 1 here now representing that switch close. Your program that you write is not looking at these switches. It's actually looking at, well, it's looking at the switches and it's updating this table right here with the 0 or 1 depending on the state of this. So if you watch right here, when I toggle the switch, when I open the switch, I close the switch. There's a 1 and it toggles from a 0 to a 1. So if I close this switch and I close the one below it, I now have 2 1s in these bit position 0 and bit position 1. And since I'm looking at this with an examine if closed, I see 2 1s there and they're ANDed together. If I change this to the output table, notice my address over here is output module 2, bit position 0. Well, in the output table, output module 2, bit position 0, there's a 1 there because both of the switches are closed and there's 2 1s on the input image table. Now, if I come over here, if you watch that one, I'm going to open one of these switches. Since I have them ANDed together, that AND is going to become false, and there's a 0 there now. Okay, so I can look at this table, any one of these tables, the radix function over here. Radix just means the base. So right now it's on binary, so it's displaying all these. Let me close these two right here. So if I close these two, and I'm going to go back to my input image table. I'm going to go back to that. So this is reading this whole row in binary. So it's going to show the actual zeros and ones of each bit position mapped to these screw terminals over here on the hardware. But I can change this. I can look at this in I can look at it in octal. So now it's giving me the octal value of that whole rung. I mean, if you think about it, if you go back to binary, even though we know these are the positions of the switches both being closed, that's still, if you look at it as a binary number, this would be a 2, and that's a 1. So this is a binary 1. A binary 1, 1 is in base 10, and base 8, and base 16 is a 3. So when I change this to octal, it's going to read 3 octal. If I change it to decimal, it's going to read a 3. I can even change it to hex. So I can look at these values in any number system I want, but just know that the actual number system stored in memory is a binary number system. No matter how I look at it, this is just changing the binary to something that I want to look at as a human. It's actually stored in zeros and ones. I notice when I change from hex, I need 4 bits, and I'll need 3 here. Well, that should be 3. I guess it's showing more than 3 because we have more. We have 16 bits. But just remember how to represent these numbers. Now, let me clear this out. Well, I got it. See, I tried to go here to new. You want to go back to program. I can go back to program, and if I want to start over again, I can do new, and that cleans everything out for me. I'm going to add another rung, so I got to go back to my edit to get to my commands. I'm going to add a rung, and I'm going to add this loop right here. I click twice, and this thing can be a little touchy, so I got this other rung that I don't need. It's not going to hurt anything, but if you want to get rid of it, you can just left click on it and just say cut. It'll get rid of it. Now this is the way I can OR. I can OR this right here. I can OR. So that if I want to add, if I go back here, let's add some more commands here. So let's say I add this, and I add this, and I add an output. Like that. So I can let's give this some I don't know, let's give this address. So we'll give this address, and we'll give this address. And so here's my OR here, and let me just get rid of that for a second. I'm going to cut that out of there. And what I want to do is change that to a push button. And let me get rid of it. So this branch right here, this gets a little bit touchy sometimes. I'm going to try to cut that out. See, it won't let me cut that out of there. So I don't know. And you'll see what I'm saying when you play. They don't have all the bugs worked out of this. So I should be able to go right click on that and cut, but I don't, let me see. I don't know how to get rid of that. I don't know how to get rid of that that OR. So you guys can play around with that and see if you can get rid of the OR. But what I wanted to do was I wanted to try to explain a little bit. So I can put this here, and then I'll give this an address, and I'll give this an address, like that. And if I download this and run it, when I press this, since this is a normally open push button, when I press that, you can see that it's going to follow. See, it's going to follow. If I have it pressed, I have logic continuity. If I release it, then it's going to, because I have I'm using a normally open button. But if I wanted to, I can come over here and now when I add this time, what I'm going to do is I'll add this. But that's not what I wanted to do. So I think to keep that from happening, if I highlight this and then click on that, it should go right. I'm screwing up here, but I double clicked on it accidentally. But what I was showing you, if you highlight this and then you double click on it, then the control will go to the one that's highlighted. Now the problem is I don't like the double click method. I don't like that, so I just like to drag. So again, I don't know how to get rid of these. It's probably a cut wrong. Let me see something. I don't know how to get rid of those. You guys can experiment and maybe tell me how to get rid of these. But what I wanted to show you was if I guess I can just move this over to here. We'll just use that one. So I can move this. I can just drag this in and out of the OR. So you can move these around. And instead of double clicking, I'm just going to put another one of these right here. I'm going to put another one right there. And now I'm going to come over here and give this the same address as the output. Now let me get rid of this. I want to show you something. If I cut this, if I give this a label, so I'm just going to give this a label. Just call it output for now. If I give this a label, and then I put a command right here that I want, you got to hit that little red. So I got the command. I can give this the same address. I can just actually drag this address over to this. If I want to make this my seal-in latch. So I got to give it the same address as this. But you don't have to type that. You can just drag it over, and when it does, it's going to carry it should carry the label with it. Let's see. When I drag that, you see it carried the label with it. So now when I come in here and I download this, so when I download this, when I push the push button, now remember before this turned yellow and that turned yellow. When I released it, then that went to false. So now, let me put this in run. When I push this, watch what happens. When I push it, both the top of my OR, both the top contact and the bottom contact are true. The top contact is connected to my normally open push button, and I'm still holding it down, so it's true. But when I release it, the top contact is going to go false. So it's false. Notice it's false, but this is still on because now when this is true, it makes this contact true. So I still have logic flow around. This is an OR. I have logic flow through here. And so I've latched this thing on. The problem is there's no way to turn it off. There's no way to turn it off. So normally what we do, when I want to program it off, what I want to use is a normally closed button. Your start-stop sequence, you use a normally open button to start it and a normally closed button to stop it. And that is a OSHA rule. If you guys know OSHA, that's an OSHA rule that you have to use a normally. The reason is if you have to disable something, it's easier to break the power if it's to open the switch up than it is to try to close it. What if you have something in between the contacts and the close position? You can't close the button. It could be something stopping the button from closing. I guess in theory it could be something to stop it from opening. But by OSHA rules, your stop buttons are always your physical stop buttons are always normally closed. So I'm going to go in here. We got to put the stop button in here. So I'm going to put the stop button in here, and we'll use this one as a stop button. So I'm going to right-click on it. Let me go back to program. I'm going to right-click on this, and I want to use this physically has to be a normally closed button. That's my stop. And so when I come in here to actually use this, here's where you can get confused if you're not careful. I can drag this over here, and I can actually put the stop button anywhere. I can put it right there if I want. I can put the stop there, and I'm going to map it to here. I'm going to map it to there. Now, what students do sometimes, they'll say, all right, well, this is a normally closed button, so I want this to be normally closed. So I'm going to change that to normally closed. That's not the correct logic. It's the correct, if you're translating this to an electrical circuit, that's the correct electrical translation, but it's not the correct logical translation. I actually want, in my input image table, I want this needs to be true all the time so that I can have logic continuity or logic flow through that switch. I actually want this to be a normally open. So it's going to look at that. So now when I download this and I run it, you see that this is already closed. So now when I push this button, and I push that button and release it, this is started. If I want to stop it, I can come down here to my stop button and you'll watch this. This will stop it. So now the motor is off. So this is a circuit you're going to make in lab, but what you got to do is you got to explain it. You got to walk through step by step and explain what each of these things are doing. And just to say it in words, just to prove to me that you understand what we mean by start, stop, and latch, and what you want to use the term logic continuity, logic flow, and all of that stuff. So the best way, guys, is just to kind of play around with this. One last thing before I sign off, this button right here. Now, PLCs do not have this scan button. This is something that's unique to the program, but you can actually speed up and slow down your program scan. So when you're troubleshooting, actually later on in the semester, you'll probably use this. Like when you're troubleshooting, you can slow it way down and kind of walk through your program to see where there's trouble. So I'll tell you more about this scan button. This is a very, very useful function for the program, but just keep in mind that you don't actually have this functionality with a regular PLC. So there's a tutorial that you go through for Lab 1. The first thing you'll do is a getting started package you'll go through. It's in your lab manual if you have the lab manual. If you don't have the lab manual yet, I put a copy of it on your Canvas for you. Download that and go through the getting started. It's going to walk you through a tutorial that explains a lot of the functions that I've talked about and some that I didn't talk about. So when you go through that tutorial, you'll know enough then to do the lab. And then at that point, you just got to understand what we mean by fill-in circuit, how it works, and what we mean by logic continuity, and be able to explain those terms. And that's pretty much Lab 1. It's not too difficult. Does anybody have any comments or questions for me before we sign off?
So I have one question regarding the final report. So it says 1 to 2 pages. Is that single space, double space, anything specific?
No, I mean, I guess technically I could tell you 1 to 2 pages, double space, and the reason is, so if I want to comment to you, I can write in between the lines and say, hey, I'm not going to do all that. Just what I want to know, I don't know who's asked the question because I'm not looking at the screen, but all I want to know is that if you can explain it in a paragraph, single space, explain it in a paragraph. But what I want is a well-explained document that lets me know that you know what we mean by logic continuity, that you know and you've explained step by step how a fill-in circuit works. You know, why do we have to use a normally closed push button? Why do we use a normally open button for this? And the addresses have to match. You want to go through and explain step by step what you're doing. If you can do it in the paragraph, then do it in the paragraph. I say single space, your report, depending on how you write, should be about a page, close to a page. But if it's less and you've done a good job explaining, you'll be okay. I'm not going to count pages. I'm going to look at your work to see if you really, from what I can read, if you really understand the fill-in circuit, how it functions, and logic continuity. If you can do it in a paragraph and a half, you'll get 100 points for it.
Okay, thank you.
Anybody else have any questions? Well, guys, thank you so much. I went a whole hour over. I really, really appreciate you guys sticking in there with me. I mean, I know I'm using your time now and not the school's time. So, but thank you for doing that. I'm just going to look to see who. Oh, wow. So, okay, I'm down to 8 people. So Nick and Wesley and David and Tate, all you guys that hung in there with me, I really appreciate it. Thank you. And if there's anything that comes up, now we won't meet. We will not meet on Wednesday. We will not meet on Friday. We'll meet next Monday. And then next Monday, your lab will be due. You have to upload it before the due date, the due time. And make sure, I had a couple people email me homeworks that were late because the link disappeared and shut down. I will not accept any labs that are late. You really want to, don't if you email it to me, I'm not going to count it, is what I'm saying. Don't miss the due date time. You want to stay on it with these labs because they're going to come fast, and I want to make sure you guys get through it, learn what you have to learn, and then move on to the next stuff. Guys, have a great rest of the day, and I will see you, a week from today. If anything comes up between now and then, please send me a text, and then we'll deal with it. Thank you.
All right. See you next week, Professor.
Thank you,
Sure.
Professor.
Have a good one.
Bye-bye. Yeah, go ahead. I have time. Oh, I thought somebody had a question. Okay, I guess they not.